Okay, class, so good day. I have decided to create this recording because many of you are unavailable due to exams. So I am going to basically crash course the topics that we have not yet discussed for Module 1 in preparation for your exam. First topic is on combinations. We have talked about permutations in our previous uh, meetings, but now we are going to talk about combinations. And I just want to summarize because, as I mentioned, this is a crash course. One key difference between permutations and combinations is that when you are counting the number of ways in terms of permutations, the order matters. This is similar to, this is what we did with the election problem, where when we first selected the president followed by the secretary, that order matters. So the first person that you select is president, the second person is vice president or secretary, I mean. But when it comes to combination problems, when you are asked to count how many ways to do a certain task, usually and typically the order does not matter. And an example of a combination problem is the committee problem, where you are asked to elect a committee of several number of persons from a certain group. For example, in this example, no, how many ways could you elect a committee of 2 persons from a set of 5 people? And when you select 2 persons from a set of 5 people, it doesn't matter who you select first, right? The order does not matter. So if you select Alfie first before Bogey, that is the same as selecting Bogey first before Alfie. It's interchangeable. And because of that, AB, as listed here, is not equal to BA. Is equal to BA pala. For permutations, for our previous topic on permutations, AB is not equal to BA because the order matters. But for combinations, AB is definitely equal to BA. And the number of ways is reduced compared to permutations. In fact, if you remember, there is a similar problem involving the same group of people. The answer for that permutation problem is 20 ways of selecting a president and a secretary. But for selecting a 2-person committee, all you need is like 10 ways. All you have is 10 ways to do that. And because the order does not matter, the use of curly braces is used instead of parentheses. That's for notation. And I just want to scroll over the symbols used for combination. So the symbols are NCR, CNR. So that's similar to the NPR symbolism used for permutation. But there's another more popular notation, this column matrix NR. This is usually the notation used for combination. And I will show you the formula. So this is the formula for when you want to solve for the combination. N factorial over R factorial times N minus R factorial. So it's quite similar to the permutation equation. If you remember the permutation equation, wala lang R prime dito. Okay? So let's evaluate, for example, the combination problem of taking 3 from a group of 10. So one example word problem would be, how many ways can you select 3 a 3-person committee from a group of 10 people. So if you use the formula, that's 10 factorial over r factorial, which is 3 factorial, times n minus r factorial, which is 10 minus 3 and 7 factorial. And again, to evaluate with the presence of this factorial, you want to expand the numerator 10 times 9 times 8 times, but you pause at 7 factorial because you know you can cancel out the 7 factorials in the denominator and the numerator. Because you are left with 10 times 9 times 8 divided by 3 times 2, which is 120. And n0, so where n here can be any number, n factorial over 0 factorial times n minus 0 factorial. So the n factorials cancel out. What you're left is 1 divided by 0 factorial, and 0 factorial is 0 factorial is by definition equal to 1. Okay, so the Pascal's triangle, if you remember what the Pascal's triangle is, it is this triangle that has the following. Let me open a Jamboard. Sorry about that. There, this is the Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and so on and so forth. And there is a simple pattern to recreate the Pascal's triangle. You simply have to add 2 numbers above it to get that number. So 1 plus 1 is 2. And how about this? No, 1 plus 2 is 3. 2 plus 1 is 3. And 1 here, because we assume there's a 0 here. 0 plus 1 is 1. And 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Right? Okay. So I hope you see the pattern. And why are we talking about this Pascal's triangle? Well, it turns out this is related to combination. Apparently, the numbers here are the answers to combination problems. So, for example, the first number in the Pascal's triangle 1 is an answer to the combination 0, 0, where n is 0 and r is 0. And 1 here is also the answer to 1, 0, 1, 1, and 1, 3, 3, 1 are 1 to 1 are the answers to the combination problems 2, 0, 2, 1, 2, 2, and 1, 3, 3, 1 are the answers to the combination problems 3, 0, 3, 1, 3, 2, 3, 3. And can you see the pattern as well for the combination problems? So expect that here we have 4, 0, 4, 1, 4, 2, 4, 3, 4, 4. And why is this relevant, at least in the field of mathematics, is because when we have this, what you call the binomial theorem, so if you have like 2 variables a plus b and you raise both of them to the nth power, you can use this theorem where n0, these are combination problems. No? We actually use combination problem to solve binomial problems raised to the nth power. Any number, second, third, fourth. Yeah. Okay, so that's my summary for combination. And to learn more about combinations, I recommend that you read our PowerPoint presentations and do your own self-study. But now I have to do another crash course on patterns in nature. And for patterns in nature, the reason why we are studying this in mathematics in the modern world, sorry about that, is because I do believe that mathematics is inspired, that the invention of mathematics is inspired by the fact that we see patterns all around us in nature. And numbers are, there are patterns in numbers, right? The ability to see patterns inspires us to try to describe these patterns and beyond the use of beautiful, amazing. So we have invented mathematics in order to properly describe these patterns. So let's just look at the patterns that we see all around us. And in fact, no, we are able to invent words to describe these patterns. And the first word that allows us to describe patterns is symmetry, which comes from the Greek word which means with measure, and it is the geometric regularity possessed by an image of object or object. And there are several main types of symmetry. The first is reflection symmetry, which uh, is also known as line symmetry, because if you draw a line, it divides the figure or object into two halves such that one half is the exact mirror of the other. And you can draw multiple uh, lines of symmetry if it works. So, for example, if you have a triangle, that is actually, the triangle has threefold symmetry, which means you can draw three lines, and for each line, the triangle is divided into three exact halves, into halves, exact halves. Rotational symmetry is another type of symmetry, that if you rotate an object, it still looks the same even if you rotate not exceeding 360 degrees. Because after all, if you rotate an object 360 degrees, it will go back to its original orientation. But there are shapes that if you rotate them even less than 360 degrees, they will look the same. So if you notice this three petal flower, the minimum angle with which you can rotate, whether clockwise or counterclockwise, the shape so that it looks the same after rotating is 120 degrees, diba? If you rotate the flower 120 degrees, it will be oriented and will look the same as its original pre-image. So since 120 degrees is the minimum angle you need to rotate that object to achieve the same look, looking the same, then it has an order of rotation of 3, which means you can rotate it 3 times before going back to 360, and for each time it still looks the same. And so the way to get 3 is to simply divide 360 by 120, which is the minimum angle of rotation. Right. So point symmetry, this is when every part of an image has a matching part with the same distance from a particular point of reference in the opposite direction. And often the point of reference is similar to the origin of a Cartesian plane. And if you position the Cartesian plane strategically, perhaps the middle of the object, you will find that there are similar points that are equidistant from that origin. So that is point symmetry. And those are the types of symmetries. I am going now to talk about another crash course discussion on transformations. And so for transformations, there are several kinds. So transformation, of course, is a mathematical process of manipulating a two-dimensional image or object. And during transformation, there are two important terms: the pre-image, which is the shape before the transformation, and the image, which is the shape after transformation. Simply moving the 2D shape is a kind of transformation, but the first one we talk about is dilation, which is the shrinking or the enlarging of the pre-image. So when you shrink or enlarge, make sure that the inner angles are retained and the lens are the only ones that are changed. For reflection, so that was dilation, and reflection is you do that by creating a line somewhere and imagine mirroring or flipping the pre-image across that line. And so you create a new image, which is the reflection of the pre-image. Rotation is when you turn the pre-image around a certain point of reference. So you select a point of reference so that each point in your pre-image is rotated the same way, and so that you can achieve a proper rotation. So shearing is when you move one side of a pre-image parallel to a side that is fixed. So as you can see here, the pre-image is a rectangle, but since we fix the lower side and we move only the upper side, so the image is no longer a rectangle, but is a quadrilateral. Translation is when you simply move the position of the pre-image, but you're not rotating it, reflecting, dilating, or shearing. So the shape and the orientation stays the same. You can also classify the different types of transformations as rigid or not rigid. And it is rigid if the shape did not change in size or the shape is not changed from pre-image to image. But a non-rigid transformation changes the size and shape of the pre-image. All right, so that's the end of our crash course in transformations. Let's talk about fractal patterns. And fractal patterns are complex patterns that are self-similar across different scales. It can be visualized as a never-ending pattern. So the way I see it is that if you look at the object initially, it has a certain pattern that you recognize instantly. But if you zoom in, you discover that the same pattern exists. So that is really fascinating. And that is something that you see a lot in nature. Even if you zoom in, you see the same pattern from the zoomed out version. These are examples of like fractal patterns that you see in nature and also the ones that are invented by human beings. So that's all I can say about fractal patterns. Let's talk about tessellations. And so tessellations are tilings of shapes in a certain pattern upon a surface such that it covers the whole plane. So imagine that you have a plane and you have an empty plane, but you intend to fill the plane with shapes without gaps and without overlaps. And in nature, you see that a lot, this pattern as well. You see it in the honeycombs. You see that the honeycombs have a hexagonal shapes that are not overlapping and that there are no gaps between. Also, you see a tessellation in the scales of certain animals, and in this case, a coral snake. So there are several types of tessellations. You have regular tessellations that are made up of congruent regular polygons. And fascinatingly, they're in two-dimensional tessellations. There are only three shapes that can be tessellated regularly, and these are squares, hexagons, and equilateral triangles. Semi-regular tessellations, so they're not regular, but they are tessellations that are composed of two or more regular polygons, wherein the patterns to which they are arranged are the same around each vertex. So you can think of vertex as intersections of lines. And if you look at the yellow dots here, these are examples of vertices. And notice that the vertices are surrounded by two triangles and two hexagons. And no matter which vertex you look at, that's the same pattern repeated. It is always surrounded by, the vertices are always surrounded by two hexagons and two equilateral triangles. In the second example, each vertex is surrounded by three triangles and two squares. So that's a semi-regular tessellation. Demi-regular tessellations are tessellations that utilize two or more different polygon arrangements around different vertices. So if for semi-regular tessellations, the same pattern of regular shapes is repeated for each vertex. For demi-regular tessellations, there are several vertices that have different shapes surrounding them, but there's a limited number of vertex. So there are only 6 kinds of vertices in this example, and for each kind of vertex, a different set of polygons surround it. But that's all, no? There are only 6 kinds. It's not like it's totally random, because if it is totally random, then you won't be able to see such a beautiful pattern. So there are 6 kinds of vertices, and each vertex is described as a kind in terms of the kind of shapes that surround it. And of course, you have the non-regular tessellations, which are tessellations that utilize non-regular shapes in its patterns. Okay, so that would be all for tessellations. I want to talk about the Fibonacci sequence, and hopefully, how much time do we have left? All right, so the Fibonacci sequence is invented by Leonardo Bonacci, and the way he invented the Fibonacci sequence is by creating a hypothetical problem and solving it. And this hypothetical problem involves two newborn rabbits, and the question is to determine the number of pairs of rabbits that can be born from the said pair. But there are assumptions. The first assumption is each newborn pair, a female and a male, matures in 1 month and then starts to breed. 2 months after their birth and every month thereafter, a now mature pair breed at the beginning of each month. This breeding then results in the birth of one newborn pair at the end of that month, and no rabbits die during the course of the year. So these are very ideal assumptions, but this is an ideal problem. So the first month, newborn rabbits. The second month, the newborn rabbits mature, and so they are able to make babies. One pair of babies. The third month, the mature rabbits are still there, but they now have a newborn. The fourth month, the mature rabbits made a new pair of babies, and the younger pair matured, so now they are able to make their own babies. And if you repeat this process, you come up with this number of pairs of rabbits: 1, 1, 2, 3, 5, 8. And 1, 1, 2, 3, 5, 8 is the Fibonacci sequence. So this is the Fibonacci sequence: 1, 1, 2, 3, 5, 8, 13, 21. Notice that the number is a number in the Fibonacci sequence is actually the sum of the previous two numbers. So for example, 34 is the sum of 13 and 21. Okay, so that's the Fibonacci sequence for you. And the fascinating about the Fibonacci sequence is you can see it in the real world. No? For example, in terms of the number of petals in a flower, they seem to follow the Fibonacci sequence. The number of petals in a flower only seem to be the numbers in the Fibonacci sequence. And also in the golden spiral. So when we make squares with the widths of the Fibonacci sequence, we get a nice spiral. So you start by creating tiny squares with width 1 followed by the width 2, 3, 5, 8, 13. And if you arrange them so that they can form a spiral. And what's fascinating about the golden spiral, which is uh, made by these Fibonacci number widths, you see that golden spiral in nature a lot, even in the face, in the shells, and even in spiral galaxies, in your clenched fist. So that is very fascinating, definitely. I only have 10 minutes for my non-premium recording, Zoom recording. So I'm gonna go to sets and hopefully I have enough time to discuss sets. But for sets, we're only talking about the basics for this term. And that means defining what sets is. So a set is basically um, a mathematical way of organizing objects. No? So the objects that belong to a particular set are elements called members or elements. And we use braces to enclose them. So in mathematics, most sets are numbers or variables, but of course, we are not limited to using numbers and variables when defining sets. We can use names of objects, for example. You can use names of objects. Also, when you list down the members of a set, that's known as the roster method. And we can use the symbol epsilon to designate that a certain number or object is or variable is a member of the set. And we also have set operations. So set operations are, for example, the equality of sets. These are not yet, these are just types of sets. Two sets are equal if they have exactly the same elements. And if you have an empty set, that means it has no elements. You use this symbol, no? Circle with a slash. So the complement of a set. So in set theory, we have what is called a universal set, which is the set of all elements that are being considered. And inside the universal set, we can talk about smaller sets within the set. For example, set A could be inside the universal set because it contains elements that are also in the universal set. And also it has elements that are not in the universal set, that are not in set A but are in the universal set. The complement of a set A, denoted by A prime, is the set of all elements of the universal set that are not elements of A. For example, if your universal set is the numbers from 1 to 10, the whole numbers, and you have a set S, which is 2, 3, 5, 7, which belongs to the universal set, then S prime is the complement of S, and it is a set that includes all other numbers in the universal set which are not in S. So S prime is all the elements of U that are not in S. So that's at 1, 4, 6, 8, 9, and 10. Remember that S is 2, 3, 5, 7. the complement of the universal set and the complement of the empty set. So the complement of the universal set is the empty set, and the complement of the empty set is the universal set. Sorry. Now let's talk about subsets. So set A is a subset of set B, denoted by this symbol, if every element of A is an element of B. So for example, number 1, you have a set A2, B4, C6. All of these numbers or letters are found in this other bigger set. So we can say that the smaller set is a subset of the bigger set. Number 3, 2, 3, 5, 7, 11 is a subset of the equal set because all the elements here are also here. So in fact, now we can say that every set is a subset of itself. So also we can also say that the empty set is a subset of every set. However, we have another kind of subset which is known as the proper subset. You can say that a set is a proper subset of another set. And if you use the symbol, as you can see, there's no line in the bottom anymore. We can say that a set is a proper subset if every element of A is an element of B, but they are not equal. So that basically means that set A has fewer elements than set B. They should not be equal. For instance, this set ABC is a proper subset of ABCD because elements ABC are also found in ABC, but they are not equal. So a Venn diagram, this is a diagram that you can draw so that you can visualize sets. So intersection. So the intersection of sets A and B, noted by the inverted U symbol, is the set of elements that are common to both A and B. So for example, you have set A, which is 1, 4, 5, 7, and set B, which is 2, 3, 4, 5, 6. And set C, which is 3, 6, 9. Find A intersection B. So A intersection B is simply what elements in A are also in B. What elements are common to both A and B? And the answer is 4 and 5. And A and C, they have no common elements, so their intersection is the empty set. So when the intersection of two sets is the empty set, you can say that both sets are disjoint. The union, on the other hand, is the set of elements that belong to A, belong to B, and belong to both A and B. For example, A union B, where A is 1, 4, 5, 7, and B is 2, 3, 4, 5, 6. So all those elements, including the common ones, are listed for A union B. So A union B is 1, 2, 3, 4, 5, 6, 7. You can use a draw. You can do a Venn diagram to do this, no? To find the solutions to intersections of sets. I guess those are the basics now. If you want to learn more, then you can simply read these PowerPoint presentations that I have prepared. Thank you very much and good luck sa exam. And thank you for your attention.